Hello, Professor. So this is my project. This is the expand coupler. It's a stripline coupler. And going to the slides. So I have designed a single section symmetric edge coupler. So the frequency range is 8 to 12 gigahertz. I have used a stripline technology instead of microstrip because in microstrip we have group delay, the different phase velocities, uh, as it is a quasi TEM mode. But stripline has a pure TEM mode, and the velocities above and below the conduction layer is the same. So the stripline coupler or microstrip coupler offers us a 90-degree phase shift between the direct port and the coupled port, and we'll see that. And I will be simulating the magnitude of S21 and S31 and their phase difference. So we have two modes in couple and couplers. That's called even mode and odd mode. When the couple lines have uh, current traveling in the same direction, then we'll have even mode, and the impedance of each line uh, is known as even mode impedance. And when the currents travel in opposite directions, we have what is called an odd mode, and the impedance of this individual line is known as odd mode impedance. So we can calculate the coupling coefficient as odd mode even mode impedance minus odd mode impedance divided by even mode impedance plus odd mode impedance. So this is my coupler design. I have two strips, and the substrate I'm using is Rogers RO4003, and here are its properties. This is the top view, the lengths and widths. So initially I used line calc to determine the width, spacing, and length of the coupled lines. Uh, but the after the HFS simulations, the result was not as expected, because whatever the line calculates is for the base. Uh, it assumes a lot. So in practical results, we'll get a different simulations, which is not as expected. So initially, I used those design values, but by using this parametric setup and optimization functionality, as you can see in this uh, figure, I used different H values and simulated for all these values. Similarly, I have simulated for different widths, lengths, spacing, and I got this design values, the substrate height, width, length, and spacing, all these values. And finally, I used optimization functionality. Uh, this optimization functionality can be I will show you a bit later. So these are my results, and this is the animation. So now going into the tech HFSS, this is the thing. So these are the four ports: port 1, port 2, port 3, and port 4. And all these boundaries are copper. I'm using a copper as conductor, as material, and I'm using a lumped port excitation. And the solution setup is from 8 to 12 gigahertz. This is the parametric setup, so I can edit and I can change these values, and if I analyze, I'll get all the results, and I can choose whichever is close to what I intend to. And this is the optimization setup. So what I was trying to do is getting S21 as 3 dB and S31 as 3 dB, and the phase difference to be 90 actually. And I got the phase difference as this. So I was getting plus or minus 2 degrees as phase imbalance. So here is the animation. As you can see, this is the port 1. So from port 1, we're getting the signal, and we can see the strips interacting with each other, and some part of uh, the signal is going through port 3, and the other part is going to port 2, as we can see. So this is my project, and I have done the microstrip as well. But the problem with microstrip is, as I mentioned, the phase velocities are different uh, above and below this conducting layer, so we don't get the results as expected. I'll show you once. So this is between 8 to 12, and we are getting less than -4, and it's going to the -6 and -7 something. So that's why I took stripline. Even stripline is not perfect, but if you're using in single section, only single section, if we use multiple sections, then we'll get a better bandwidth and better performance, overall performance. So this is it, Professor. Thank you.